Welcome to my Introduction to Networking course, also known as ITN. This is the version 7 material preparing learners for the Cisco CCNA 200-301. Cisco curriculum, everything is owned and copyrighted by them. So, moving on, we have our IPv6 packets. First of all, why do we have IPv6? Mainly because there are limitations for IPv4. Basically, IPv4, we're losing addresses. They are being depleted. In America, we still have lots of IPv4 addresses, but globally, those addresses have basically been exhausted. Also, end-to-end connectivity is not there. Each home has private networks, meaning each of those private networks actually have a technology called NAT, so that it takes these private addresses and get them a public address. I've already explained NAT in other videos, so if you have questions on NAT, shoot me a message. I'll send you the video on NAT translation. Essentially, NAT takes private addresses and converts them to a single public IP address. Well, that does not allow for end-to-end connectivity, because if your router is actually NATing those addresses, we don't know what behind that router, which device is actually sending that communication. Only the router does. That is what it means by lack of end-to-end communication. IPv6 actually allows for end-to-end communication without the use of NAT. Why? Because IPv6 has way many addresses. IPv4 has a few billion addresses. Well, IPv6 has a few undecillion addresses. So what is the difference? There are 3 undecillion grains of sand on our planet. And IPv6 allows for 340 undecillion addresses. So just to give you a scope of how large an undecillion number is, they're huge. Versus IPv4 with their few billion addresses. So IPv6 has way more addresses, so increased address space, no longer needing some form of address translation, and most importantly, packet handling has definitely been improved by a simplified header. So we already seen an IPv4 header and what that entails. So let's go ahead and look at an IPv6 header. While IPv6 header may be larger because of the address spaces, you'll see that it's not as bloated. We have a version, we have priority, we have flow, we have payload length, that's the entire length of the packet. We have a next header, basically that's the higher layer protocol. We have a hop limit, that's the TTL, and we have source and destination. Several fields have been removed from the IPv4 header because they were not needed. Version, again, IPv4 versus IPv6. Traffic class, again, priority. Flow label is basically how the device will handle identical flow labels. Basically, you can try to manipulate this for prioritization. It's not quite the same thing as QoS, but you can do different flow labels to say this may be the same priority as these other packets, but do this functionality. Payload length is again the payload of the entire packet. Next header is again upper layer protocols, hop limits, the TTL, and source and destination. IPv6 addresses, not IPv4 addresses. Again, here we're talking IPv6. So these are IPv6 addresses, not IPv4 addresses. And again, the size of the address dictates that. IPv6 packets can also have a extensive header, an EH, Part of EH characteristics is basically provide optional network layer information. Again, they're optional, and this is placed between the header and the payload. And this may also be used for fragmentation and security. So unlike IPv4, routers do not typically fragment IPv6 packets. They use much larger packets. So now that we have a good understanding of how the routers route the information using IPv version 4 and version 6 options, how does the router actually take that information and use it? Now that we have a good understanding of the different characteristics for the two versions, how do they make decisions? So packets are always first created at the source, first of all, meaning the source will dictate where it's going, the destination. So each host device will create their own routing table. Each individual computer actually has a local route table. If the information is to leave that network, it needs to be sent to a default gateway. That will be on the LAN. The nice thing is, to leave our personal LAN, our own personal network, we have to send it to our actual IP address. By default, the device will actually communicate with its link local address. That is abbreviated 127.0.0.1. That's just a clever way of saying, look at yourself. That is part of the local host. If you want to communicate with other local hosts on your network, that's going to be outside of your own personal network. We have to use our actual IP address, not our loopback address, 1. And 2, we're also going to be using our physical addresses, our MAC addresses. If we want to communicate with a remote host, we will still be using our IP addresses, but this time the destination address will denote that's not part of our network. It will have to be sent to our default gateway. That will be our exit point for our network. That will be part of the router. That's what the router's job is to take data from one network and transmit it to a different network. We will still be using our MAC addresses for that local connection. We will send our packets to our router, but how do we do that? Basically, what we end up doing is we'll take our packet. Before we send it on our medium, we will create a data frame, typically an Ethernet frame, and our frame will have the source MAC address of our device and the destination MAC address of our router. That way it knows to send to our router. Our router will receive the frame, look at the frame, tear it off, look at the packet, and from that packet it will make forwarding decisions. So the source device will determine whether the destination is either local or remote. If it is remote, it has to go to our default gateway. Basically, this is done by looking at the IP address, looking at the subnet, and seeing if it's attached to the same network ID. If it's not part of the same network ID, send to default gateway. So what is a default gateway? Basically, a default gateway is a layer 3 device. It has to have a legitimate IP address in the same network range of your LAN. It will accept data frames from the LAN, and it will make forwarding decisions on which path to take to the remote host. Basically, it provides the routing functionality to go to itself to a remote network. If a network has no default gateway, then no connectivity outside of your local network. So a host will know the default gateway either statically or dynamically. You can manually assign default gateways or make it part of the DHCP process. IPv4 uses those two functionalities, where IPv6 will send a DGW, it's a default gateway, through router solicitations. Basically, the router will say, hey, this is my address, and it will solicit all of the devices on the network using RS messages, or can also be configured manually. The default gateway is a static route, and it is also known as the last resort route in the routing table. Again, the purpose is, if it's not part of our network, send to default gateway, and it will figure out what to do with it. So what does our routing table look like on our hosts, on our computers? We could do a netstat TAC-R, and you can see the route table it has. Here we have straight zeros. That's going to be our default gateway. And you'll notice that it even has a gateway column that all zeros go to. Basically, it's a clever way, if you don't know where to send it, send here. And then we have other matching portions, and that will tell you where to send them and the metric used. So we have destinations, we have our net masks, we have our gateways, interfaces, and metric. Again, metric being the cost of how to send the data. Metric also being the lowest one is the most preferred. And that is this chapter in a nutshell. If you have any questions or concerns, please reach out.